is the space or the memory which you need to store that forwarding table. So large tables will require large web, which obviously costs more, and there are several engineering real estate on the chip kind of constraints that browser manufacturers or vendors they have to maintain. So large tables will require larger web memory to store. And just to give you an idea, the web memory is not something like the memory that we all computers. This is the more orders of magnitude more expensive than that memory that we see. Another concern, which is a significant concern for the service provider community, is that the stable growth leads to memory upgrade. What happens is that the put memory to the router just to hold enough entry into the table with a projected growth of the license so maybe 3 years or 4 years. After 3 or 4 years, the service provider still needs to use those routers. What they do is that they go through the memory upgrade process, which is really expensive because it requires significant hardware across thousands of routers. Large service provider can have 2,000 routers on the table. So what I present here is a scheme called reducing the size of the router table, which addresses all of these reasons. So the first concern saves the 25% on the memory lookup speed. So that means you can operate the router.
This is a proposed more definition by the US Foundation.
And in terms of memory, saves about 5% of the memory for and I'll talk about those cases as well. So to give you the background on table size reduction, I'll start with this abstract model of the router, in which a router will receive two routing protocols from other routers and will store those in routing space or rest. The best selected routes that each of the destinations will be forwarded or downloaded to the forwarding table or forwarding information. This downloading is done through a storage and lookup line. Some kind of storage and lookup is involved in downloading those best routes selected from the list and downloaded in the plan. So this storage and lookup is also responsible to forward a packet when it is received in the proper direction. So the process of lookup is longer prefix might be related to that, but a longer prefix algorithm which is built into the storage and lookup first and side on the page of the So in the last 15 years, the focus of these storage and lookup schemes is basically time and space. How much memory do you need to store that table, and at what speed you can do a lookup and update of those.
This was the first effort in making.
So the information which is downloaded from web to the web has this storage and lookup. That information is considered as a bit of what cannot be shared. However, what we argue is that this information is modifiable. You can change it carefully. If you don't want to change it haphazardly, but it is possible to change that information carefully. And that leads to reduction of the price when these routes are downloaded. So this reduction in table size can be done in the world. There was one scheme which was about 3 years ago about virtual application. So basically divide and conquer strategy. Divide it into smaller portions, deploy those smaller portions onto different routers. It requires coordination among the routers and very complex. Now, what we talk about today is aggregation with small-cap, the scheme that we have proposed, and in this case, we maintain the entire table, but we try to reduce the size of the table by combining these prefix entries into the table. So, what is this prefix aggregation or prefix combining for reducing the number of entries? So, we take an example of an internet routing table showing two entries, two prefixes X, Y, Z, 0, 0, and then there is not yet where to mean the slash 26 prefix, 26 slash prefix, and the next hop destination for that prefix is 1. Similarly, there is another entry which is in the numerical vicinity of that. Also X, Y, Z, 1, slash 26 prefix also directed towards the ball. Each of these entries covered in IP space, IP address space of 64 addresses. Last exhibits are down to this So since both of these prefixes are in the numerical vicinity of each other, only different the last bit, and they are directed towards the next hop, I can make a case for combining these two and aggregate these two prefixes without making any changes to the routing table. The functional behavior of the first table and the functional behavior of the second table exactly. This is what we call the So our goal is to do some aggregation while maintaining the semantic equivalence of the routing table. So these two tables are semantic. Let me just show this table in the form of a tree. This is how you will perform the lookup update into the tables within the route. So those two prefixes are again shown as sibling nodes here, where the next information is within the node, and the position of the node in this tree tells you the prefix. The lower nodes they denote longer prefixes, and the nodes which are higher in the tree they denote short. The IP space covered by each of those is 64 addresses. And now what we can do is that in this case we can combine those two as we did in the last example and move the two prefixes into a smaller prefix of length 25 and covering the same IP address. So this is the case when you are aggregating the sibling nodes with the same next hop and the same next hop. And the reason that we were able to aggregate or combine these two prefixes was the next hop information was the same and they were in the numerical system. Okay. To give you another example, if there is a prefix node which contains the one first line 26 line prefix, there is another one which is up in the tree, is 25 line. Now, you might notice that in the bigger space of 128 addresses, this smaller is covered within that. I can make a combination of these two again and just come up with one single prefix addressing all those 128 addresses. In this case, in this example, what we have done is that aggregated more specific prefixes into the letters. So in both of these examples, two entries, which are the two ones on the left hand side, they have been aggregated or combined into one single entry, leading to a smaller forwarding table. Now, this kind of scheme is extendable to the entire table. All those 380,000 plus entries that we have in the present day Internet routing table, we can extend this scheme to that right. And in fact, there exists a scheme for that as well. So recapping the basic aggregation scheme, you can remove the specific. Those two entries have been aggregated into one, and in the second example, the two sibling entries have been combined. Now we can exploit these kind of aggregation opportunities. These are only just two examples. There can be many more examples of combining these two. We can aggregate these prefixes over the entire table, and there actually exists an optimal scheme which was invented not very recently, actually 12 years ago. This was invented by people at Microsoft Research, invented in 1999, arranging the prefixes in the form of a tree. So I'm showing an example where there are 4 prefix entries, and within the nodes you have the next hop destination, and all the prefixes are shown here. So this table, which is represented by the tree, contains 4 entries. This scheme called ORTP performs 3 passes over the entire tree. And this can be a huge tree. We have 32-bit IPv4 addresses and 28-bit IPv6 addresses. It can be a huge tree. In the first pass, you will find normalization behavior to each of the nodes. In the second pass, you will find the next hop, potential next hop to the node, and in the third pass of the tree, you will find these entries, and you come up with a tree which is optimal in the sense that it contains the minimum number of entries that you can ever get. There is no other table that you can get which will have less than 3 entries and is semantically equivalent to the first. Now, this scheme works very well, and it could have been very nice. Unfortunately, it didn't get into the routers for the reason that I had just explained. explained that you have to go 3 passes over the screen. Now, this would not be a problem if you had to do this operation only once, but unfortunately, we have updates in the routing table. So every time we get updates into the routing table, we have to perform these 3 passes of the tree. This is a intensive process, consumes power, and vendors try to ship routers with as minimum low power requirements as well. So how do you incorporate the BGP updates, which is the routing protocol which you get the routing updates? The first option is that you have the original table, you apply the optimal ORTC scheme, you will get a table. If an update comes through, you will apply the ORTC again, get a new table. Doing this with every possible update, which can be several in 1 second, you will run into trouble because you have to do 3 passes of it. So this is an optimal scheme, but it is impractical. That's why we will get into the practical. What we are proposing is that you have this original table, you apply this one of the optimal schemes, or you can borrow the scheme from ORTC. If you do borrow the scheme from ORTC, you apply Snapdragon, get a table. If there are updates which are received, incorporate them in an incremental way directly into the table. You might go into some optimality, and we'll see how suboptimal you get. But it's a practical scheme. It takes very small amount of time, and we have results for those as well, to get incorporated now. So, summarizing, Smallband uses the ORTC, which is the optimal algorithm, through a function called snapshot function very frequently. For example, I will restart after 2 hours, let's say, and after, let's say, 200,000 updates. And then there is this update function, which is used to incorporate the entries in an incremental way into the forwarding table. So these two routing announcement or bit draws that we can receive, these are the only 2 possible kind of updates that we can receive from the BGP routing protocol. Both of those are handled through these update functions. So I won't go over the update function. It's given in a paper which is available online. Instead, I will give you an example in which I'm showing you semantically equivalent trees. This is the original table on the left side and aggregator table using Snapdragon on the right hand side. Let's say an announce is received and somebody, an external entity, wants to change the next hop information for this particular node. Similar kind of announce must be incorporated into the aggregated table. In the case of original table, it's fairly easy, as it is done in present day. And just simply update the prefix node, replace that 2 with a 4, and you are done. If you try to do the same thing with the aggregated table, unfortunately, this leaves these 2 tables on the bottom semantically unequal. Which means that the routing behavior that you want from the table, you won't actually get. What you need to do is that you need to do some local repairs, and these local repairs incorporate changing the next hops of some nodes, removing the next hops of some nodes. The algorithm which is in the background actually does exactly. So this is an example which fits the BGP announce, and similar kind of example can be given for BGP bit forward. I will skip that and go to the experimental results, some of the experimental results that we have got from the real world routing data. First, I will go over the data sets. What kind of data sets? The first data set is obtained from a large tier 1 service provider in North America. I can't take the name of the service provider, but if you look at the paper, it's very easy to guess what service provider. So the data that we were able to get from these routers, and this service provider has about 10,000 routers in India. We were able to get the 5th table snapshot from the customer access routers. Customer routers or access routers or customer access routers. Yeah. We were also able to get the RIP snapshots from the internet gateway routers or the government system border routers or internet gateway routers or border routers. All these names are used in each name. We were also able to get the BGP updates from these internet gateway routers, and for these results that I'm going to show you, we'll use the 12-hour trace from the BGP. Then we also have the route views data. Route views is the project started by University of Oregon, and they provide routing table data available to the public. And this data consists of every 15 minutes they take a snapshot from the internet routing table and dump it, provided it on the website. Since 2001, we have all these tables available within 15 minutes. And in between those 15 minutes gap, there is a BGP trace which is also available to us. And all these are available for free. Anyone can do that. So these two data sets, I come to some of the results that we have. So first of the results is reduction in the number of entries and reduction in the memory that you need that you will get in the router. So in particular, I will talk about the effect of the unique number of interfaces of the router. So for the route views data, we notice that the solid line is showing the reduction in the number of the prefixes. You can notice that with about 48 next hops, which is the far right corner, the solid line is showing about 45% of the size of the list. So that means there is a 55% reduction from the size of the list. The dotted line is showing the reduction in the memory. It's slightly higher. And the gap between these two figures depends on the storage and lookup. And the storage and lookup speed that we have used is called 3-bit max speed, which is used by the most router vendors for their high-end routers. Cisco has open effect that we use that. Unifier and other vendors, they probably use a similar kind of a scheme, but this 3-bit max scheme is used by the high-end routers. So next, I'll show the effect of unique number of interfaces with the service provider. In the case of service provider data, we notice a similar kind of a trend. As you decrease the number of interfaces, you have less and less aggregation, but still about 50%. The curve at the top is showing at the bottom is showing the savings in the number of prefixes, and the curve at the top is showing the savings in the lookup time, which is measured in terms of the number of memory access. And again, the gap between these two depends upon the storage and the lookup. Again, we have used 3-bit maps. So the largest router that we saw in this case, we used in producing these results, had more than 600. So for internet gateway routers, we got about 25% fewer memory access, which means that you can make your routers 25% faster. The lookup time would be 25% smaller when using cable. Now, those are the results only for the static routing cable. You get a snapshot of the routing cable, how much aggregation, how much saving is there. Now, when having said, you also need to incorporate these updates. This curve is showing the number of updates into the router. So along that, I'm showing the number of updates, 180,000 updates collected over 12-hour period in the service provider network. So the point where the red and blue curve, they are joined together, is the point where both of them are optimal. The red curve is showing the perfectly optimal curve. You can do better than that. After incorporating every single update, you will apply the ORDC optimal algorithm. You won't do that practically, but for the sake of producing this result, we were able to do that. And the blue curve is showing the plasma curve, using which you are drifting away from the optimal. But in this case, you notice that after 12 hours of update rate, with 180,000 updates, we lose about a couple of percentage points in the amount of activity. Go from 37.5% all the way up to 38 points. After 12 hours of update. So number of aggregated prefixes near optimal. They don't remain optimal, but they remain near optimal after 12 hours. Great. So recap and insight. What we have seen so far. The first question is how far aggregated you are after incorporating an update, and we saw that after 12-hour trace, you are pretty close to the optimal. You lose less than 2% of the fully aggregated. So numerous tables, numerous problems. Now, how does the number of peers affect the extent of aggregation? In this case, we saw that you increase the number of peers or increase the number of interfaces, you get less and less aggregation, but still in excess of it. The third important question is how many, if we want to implement this scheme in a real world router, is how many RIP-to-SIP changes or RIP-to-SIP downloads do you need for each update? For that, we need to consider the abstract model of the router again. We receive these routes from the other routers, it's stored in the RIPs, best are selected and downloaded into the RIPs. So each update, each external update into this RIP box can result in at most one change in the original table. At most one change in that. For each such update, I will have exactly one download from zip to zip. But if Malta is used, you can have either 0 or 1 or more downloads. On average, we measured all these routing tables. On average, we have less than 1 zip to zip changes, which is very good. If it's for 10,000, then no vendor would like to implement it. But if it's on average less than 1, then it's pretty enticing for the router vendors to implement this. So this curve is also showing the total number of zip to zip changes. Along the x-axis, I'm showing the number of updates which is consecutive calls to the optimal snapshot function, and along the vertical axis, I'm showing how many changes do you need. And in this case, we notice that we call the optimal snapshot function every 40 minutes, then you get less than 1,500 updates going from the list. What is the cumulative zip changes? I'm not showing the curve here, it's given in the paper. It's smarter calls snapshot every 2 hours. We get approximately 130,000 zip to zip changes or zip to zip downloads for 180,000 approximately 180,000 zip updates, which means on average you have less than one. So summarizing, what are the main findings of this work? We save with memory or line card memory 35% upward. Could be as large as 75%, depending on how many interfaces the router has. The number of prefixes is 12% better than the saving memory by using the 3-bit map lookup scheme. The loss with the incorporation of the BGP update is insignificant after day-long update, less than a couple of percentage points. And the savings in the lookup time is 25% back. The update processing changes is less than 1/15 for each step of this. The contributions of this work is we have this incremental update algorithm fully specified with their proofs, and we have these forms of proofs available in the paper as well. Evaluation of smarter scheme on real-world routers, and we also have an implementation of this scheme in Quagga router, which is a very famous router used by many providers. This is software router. The reason that we implemented here is wanted to demonstrate how easy it is to implement this scheme in a real world. By the way, Quagga follows a similar kind of architecture as is used by Cisco systems. So it's less than 2,000 lines of code incorporated in Quagga. So it's possible for the vendors to incorporate this scheme into their routers with not too much effort. The features of Quagga is that there are no protocol changes required. You don't need any protocol changes. The community is very hesitant to bring any changes to the protocol. It's a very long effort. So if we use Quagga, there is no protocol change which is needed. It's practically deployable, and the router which implements Quagga sees immediate benefits, even if the other routers in the service provider network are not implemented. So it's a local benefit. If other routers implement the scheme, they will benefit themselves as well. But an immediate router, a router which is implemented Quagga will see the immediate benefit right now. So this work, I just want to mention that this work is also being considered for standardization at the Internet Moving Transport, IOTS, the body which standardizes protocols and Internet. And this is also work that I recently presented at a conference. The conference are available on the website because I'm also interested in finding out more about this work. The details are given there. There is more detailed technical report available on my website. You can go for that. And with that, I'll be happy to answer any questions.
Anybody with any questions? No questions? Either everybody understood everything he said, or let's not go with the second option. Yeah, okay, good. Thank you, Vivek.
Yeah, but this is to formal proofs. Did you prove them by student proving, or you have some mechanical way to prove it?
The proofs were too long, and the paper allowed only 12 pages. So we are given the outline of the proof in the paper itself, and the detailed proofs are given in the technical report, which is referred from within the paper. So the formal proofs are available. In fact, in the beginning, I showed all the collaborators who worked with me. One of the guys is I myself would not be able to do that in that much detail. I work at it. So we had this guy who collaborated with us while I was in he helped us a lot in writing.
Any other question? One, this mic.
My question is, that it's practically deployable. So, suppose if we have some routers, then how can we basically embed that your smarter account?
When I say practically deployable, that means it's a simple software upgrade. You don't need to change anything in the hardware. Router vendors, they do have these kind of trees that I was showing here. They actually store the prefixes in the form of trees. That tree-bit map is the algorithm which is used for storage. So it's the tree which is already present there. All the aggregation is done within that tree. You have a separate tree for that. By just using a software upgrade, you can make sure that a router is equipped with smart RAM. And yes, and then you can enable it by using some command line. Something like that.
At one stage, you have done aggregation. You have combined the both IP addresses into one and passed down on the bottom side. At down the stream, you have got a router where you have one destination on one interface and other destination on the other interface. So at that time, you have to do aggregation. So to convert that, to find that destination. So don't you think that will become the bottleneck?
Yeah, unfortunately, that will not become the bottleneck. The example that I showed here only showed that the nodes are moving up the tree, which indicated two opportunities to aggregate the prefixes. There are several other opportunities that I will not show for the sake of time, which allow you to de-aggregate the prefixes first and then aggregate the prefixes while still maintaining the routing correctness between the tables still remains semantically equal to each other. In that case, although you are doing de-aggregation, but it's not a huge task. So, for example, for incorporating these updates to measure the maximum amount of time on a core to duo hardware, which is very similar to the hardware which is used in present-day routers. It took about 3 microseconds, which is absolutely nothing. Every vendor will be happy to go with 3 microseconds. Sorry, I can't hear you. Yeah.
So when you are aggregating the IP addresses and changing the prefixes, what is the key role of authentication of the largest prefix? Like you have changed the prefix to a lower order. You have changed it from 26 to 25 in your example.
That's right.
So what is the aggregation that goes wrong? Due to any reason, any miscalculation, what the prefix goes wrong? If a border gateway protocol router announces an information that is not valid with a longest prefix. So don't you think that it will become that network will go down?
Yeah. So in BGP they have security mechanism. Unless you authenticate yourself, they will not accept your prefixes. Normally that should happen. What happened with YouTube 3-4 years ago, that was a different story. But in BGP they have mechanisms in which you authenticate. If somebody is announcing a bad prefix anyways, even if you don't have aggregation scheme, you are still going with that bad prefix. So the scheme itself is not introducing any incorrectness. If external entity is advertising a bad prefix, then you have to live with that bad prefix.
Any other questions? Okay. Thank you very much, Dr.